So basically, this is the design for a 4 cross 1 mux. So these are the logical level representation, logic gate representation of a 4 cross 1 mux, where we have four inputs: I0, I1, I2, I3 are our inputs, and S0, S1 are our select lines. Okay, so these are our select lines, and these are our inputs. Okay, so basically, I hope you are aware of the multiplexer behavior. Okay, so let me briefly introduce you with the multiplexer behavior. So for a 4 cross 1 mux, okay, here 4 represents the input and 1 represents the number of outputs. So for a multiplexer, the number of outputs only will be equal to 1. Let's say this is our output Y, and these are our inputs I3, I2, I1, and I0 are our four inputs, and select lines are S1 and S0. Okay, so these are our select lines and these are our inputs. So what happens if our select line S1 S0 is equal to 0 0, then our output will be equal to I naught. Okay, so how to decide whether our output will be equal to I naught or it will be equal to I3? So for every multiplexer there will be a notation like this: 0 1 2 3. Okay, so when select lines are S1 S0 is equal to 0 0, then output will be equal to I naught. That is the representation of 0, the pin which is associated with here 0. So if the representation is like this: 0 1 2 3, then this I3 will be selected. Okay, so you should be careful with this particular notation, okay, or the representation. You should be very careful. So sometimes they will be given 3210 or 0123 also. Okay, so you should be very careful which pin is associated with which number. Okay, so when S1 S0 is equal to 0 0, then my output will be equal to I0. And if S1 is 0 1, then my output will be equal to I1. And if it is 1 0, my output will be equal to I2. And if it is 1 1, my output is equal to I3. Okay, according to this particular first notation, my outputs are I0, I1, I2, I3 respectively whenever my select lines are 0 0 0 1 1 0 and 1 1. Okay, so basically a 4 cross 1 mux is like a switch. Okay, depending upon the select lines, we are going to select which input we want to connect to the output. Okay, so that is how a multiplexer works. Okay, so is it clear? So depending upon the number of inputs, so we can find out by using the formula 2 power n, where n is the number of select lines. For a let's say if 2 power 3, which is equal to 8, so for 8 cross 1 mux, the number of select lines will be equal to 3. And for 4 cross 1 mux, 2 power 2, which is equal to 4, there will be 2 number of select lines. Like that you are going to decide how many select lines are there for a particular design. Okay, now, so in this particular design, what we are doing, uh, here S1 S0 we are connecting to the NOT gate, as well as we are taking it individually without connecting it to a NOT gate. So here we will get S1 bar, and here we will get S0 bar. Okay, and I0, I1, I2, I3 is connected to the one of the inputs of the AND gate. And here, can anyone tell how many wires we need? Let's see how many wires we need in this particular design. So here the output of NOT gate is connected to this particular AND gate. So we need a wire here W1, and here also we need another wire W2. Okay. So the same wire is being connected to this AND gate, and here also the same wire is being connected here, and here also the same wire is being connected. Okay. Now, so here two wires, and here there is third wire W3, W4, W5, W6. So total we need 6 wires. Is it clear how to calculate the number of wires? So we need to implement this particular design using the gate level modeling. Okay, so we need to design this particular 4 cross 1 mux using the gate level modeling. And as discussed in our previous sessions, since we have not discussed the behavioral modeling, so we are not aware of the blocks like always block, initial block. Okay, since I have not explained you till now, so we cannot able to design the test benches. Okay, so you should wait for completion of that particular behavioral modeling, then only we can come back and we can test the functionality of this particular design. Okay, So for now we cannot test the functionality of this particular design. Okay, so please remember that. So we are going to check the functionality of the design also after completing the uh, behavioral modeling. Okay, my screen is visible to everyone, right?
Yes, sir.
Yeah, let me zoom in. So what are all the input ports we have? Input
Sir,
I naught, I1, I2, I3. Okay, so these are the input ports we have: S0, S1, I0, I1, I2, I3. Okay, now I have one question here. So let's say if we are implementing a 16 cross 1 mux, then how many inputs we are going to have?
selection. 18 inputs. Sorry.
Yeah. So
20 inputs.
total 20, right? And okay, so if we have a 32 cross 1 mux, then how many inputs? Take the select lines apart. So how many inputs? Like how many inputs we will have apart from select lines?
32.
Right?
32.
So if you have 32 inputs, so what you're going to do, like you're going to write everything like this: I4, I5, I6, so on 32, or whether is there anything you can do for that?
I think vector we can use.
Yes. Okay. So in that case, vectors are useful. Okay. So basically, what we can do is, instead of writing all the 32 names, okay, from I0 to I31, we can basically use a vector. So how can we declare a vector? Let me erase this. So basically, let's say if we have a 32 cross 1 mux, okay, then we have from I0 to so on I31. Okay, so instead of writing all these names, what you can do is you can simply declare a vector: input 31 down to 0 I, or you can give any name. Okay, like this you can create a vector. So is it clear? What is your task is, I will show how to implement a 4 cross 1 mux using simple I0, I1, I2, I3. So your task is to create a vector. Okay. How you will create a vector? Input 3 down to 0. You can give any name. Okay. And instead of writing everything like this, you can use the vector and you can design your circuit. Okay. This is your simple assignment. So anyways, I will discuss how to use this vector. Okay. So if you can try doing this, you can try. Okay. So in next session, I will show how to use this vector. Can everyone try this? So these are my inputs, and coming to my outputs, how many outputs I have? Only one output. Okay, so these are my inputs and outputs. Now, so I have to declare 6 wires: wire W1, W2, W3, W4, W6. Okay, so these are my wires. Now what should I do? Now I should take my outputs, that is W1 and W2, from S1 and S0. Okay, so I'll use a NOT gate. N1, my output is W1, I'm taking it from S0, and another NOT gate, I'm taking it from S1. Okay, so this is how I'm taking my output of NOT gate. So what I'm doing, basically I'm taking the output here, W1 and W2, which are nothing but the output of this S1 bar and S0 bar. Okay, now the output of this first AND gate is I naught and with S naught bar and with S1 bar. Okay, so instead of S naught bar and S1 bar, I should use the wires. Okay, so how to use that? And E1 and the output of AND gate is also a wire. Okay, W3 comma W1 comma W2. Okay, so this is how I'm going to describe my first output of AND gate, and even W3 W1 W2. Okay, let's say this is W2 W3 W1. So is it correct or wrong? Here I will write W3. First I will write inputs and followed by output. So is it correct?
No, sir. Sir, first will be output, then input, I think, in
Yes.
the hand.
Yes. So do remember, for all the logic, all the primitive gates, first we should mention the output. Okay. First we should mention the output followed by inputs. Okay. So please remember the syntax. First is output followed by inputs. Okay. Please remember the syntax. So first is output followed by the inputs. Okay. So here W3 is your output and W1 is one of the input and W2 is another input. Okay. Next.
Sir, I not.
Sorry. I not also. Comma I not. Okay. It is a three input AND gate, right? Yeah. Next. Next is I1 and with S0 and with W1. So what we'll write, and A2, our output is a wire W4, and with what we'll get, I1 and with I1 followed by here we will get S0 directly and W1.
W1.
W1 and S0. Okay, so this is the output of my second AND gate. Okay, next, and A3, my output is W5 followed by I2 followed by S1 and W2. Okay, next is and A4 W6 comma I3 comma I will get S0 and S1. You can reverse the order also, no issue, because it is AND gate. You can use OR gate or 1. Okay, your output is Y followed by, so how many input OR gate it is? 4 input.
Four input.
Okay, so all the wires should be given here. Okay, so what are all the outputs you have? Wires W3 W4 W5 W6. Okay, so this is how you are getting your output Y. Is it clear?
Yes, sir.
Okay, and what is the data type of Y? So whoever telling it is a reg data type, so please once again reverse the concepts. So by default, the input port, or it may be an output port, it is of type net. Okay, if we mention explicitly it is of rich, then it will be of type rich. Okay, so this we have already discussed in our previous sessions, right? So please revise it. Okay, no issue. Now uh, what happens if we give here rich input, rich S0 S1 I0 I1? So what type of okay, so here you can see the red line, right? So here you can see the red line, right? So it means you have an error. So what type of error you are getting? Non-net port S0 cannot be of mode input. Okay, so input cannot be of reg. It means input cannot be of reg. Okay, so that is the meaning for that particular error. Okay, so in that we have discussed one block diagram also, right, where we have seen the connection rules, port connection rules. Input should be of only wire type and output can be of net or reg, that we have seen, right? So this you should be careful when you're designing your circuit. Okay, so is it clear for everyone? Regarding this tool demo video also, I will plan one session. Actually, I'm busy with some other works, so I will plan like using Vivado. We can do multiple things. Actually, it's not for editing or some simulation purpose. We can do a lot of things using Vivado. It's a very powerful tool actually. So I will plan, and I will once prepare the content for this, and I will post it. Okay. So for now, we will see the simulation purpose only. Like we can do many things using this. So first, let me synthesize it. So until it gets implemented, let us see some questions. So let's say we have a positive H D flip flop. Okay. So let us take a simple flip flop only. Let us take a positive H D flip flop. Okay. So let me draw the diagram for this also. D Q Q bar. This is my input, and this is my clock signal. Okay. My first question is, what is meant by a positive edge D flip flop? Like what it means. So basically, a positive edge flip flop means whenever the input is applied at the positive edge, then only it will get sampled. Okay. Other than the positive edge, the input will not be sampled by the flip flop. Okay. So let's say this is your clock. This is your clock pulse, and this is your positive edge, and this is your negative edge. Okay. And whenever if you apply the input, okay, in this case particular D is your input, so whenever this D is applied at the positive edge, then only it will be sampled by the flip flop. Okay. So other than positive edge, if you apply the input at negative edge, it will be not recognized by the flip flop at all. Okay. So if you apply the negative edge also, it will be not recognized by the flip flop. So if you apply a pulse starting at negative edge, and if you make it 0 before coming to the positive edge, so this pulse will be not recognized by your flip flop. Okay. So it may be 1, input may be 1, but output will not be changing its previous state. Okay. So here you should be careful when you're designing or you're working with a flip flops. And can you know that are you aware of the difference between the synchronous reset design and asynchronous reset design? Synchronous and asynchronous reset design. So what is meant by synchronous reset? My first question is, what is meant by synchronous reset? So what is meant by synchronous reset?
It will forcefully make the output zero, not depending upon any edge.
Synchronous reset. Okay. Synchronous reset. So synchronous reset means this particular reset signal is synchronous to the clock. That means if it is a positive edge triggered flip flop, then if we apply the reset at the positive edge only, the flip flop will be going into reset state. If it is a negative edge reset, if we apply the reset signal at the negative edge, then the particular design is going to reset state. Okay. Other than that, it is not going to reset state. Okay. And if it is a asynchronous reset, then now,
Sir,
yes.
for for asynchronous reset, will it reset at that instant or after a clock pulse?
That is a propagation delay, everything that concepts will come into picture.
Okay.
Yeah. Okay. Here, what we are discussing is a ideal manner. Like we are not going into the propagation delay, setup time, everything we have not discussed. Okay. Just we are simply
Okay.
discussing the basic concepts.
Without any propagation delay in general.
Yes, yes. Reset to clock, Q delay. Some we have some type of delays in sequential circuits. Okay. So what was my question was, so we have seen everything like about this flip flop D, Q, Q bar, and a positive edge clock. Okay. Somewhere I think yeah, here the design is also present. So this is a design for a D flip flop. Now tell me, can we model a positive edge D flip flop or negative edge D flip flop using the gate level modeling? Can we model a positive edge D flip flop or negative edge D flip flop using a gate level modeling? So this is a design which was using only NAND gates. Okay. So how can we model this particular design should work on the only the edge, not on the level. Can we achieve this particular requirement using the GLM? What I'm telling is using the NAND gates we can model, but it will not work on the edges. Okay, this particular design, if we perform in the GLM, okay, using the GLM we cannot achieve the uh, yeah, we'll come to that. So basically you can try all these designs. You can please practice, okay, so don't neglect it. So practice is very important. Don't neglect it's a simple or easy. So once, only for once you try all the codes which are in the GLM, at least you try only for once, okay. So you can create your own folder, like a GLM folder you can create and practice all this codes. I have already shared the PPT, okay. You can refer the diagram and you can practice the codes for the GLM modeling. And after we have discussed how to write a test bench, you can come back and you can write the test bench for all the codes you have written. Okay. So is this clear?